The subject name is compiler design. Previously, we discussed some of the concepts which are related to this subject, but the concept of optimization, that is the phase code optimization, one of the important phase in the compiler design. After that, the code is sent to the code generation phase. So whatever the code that is delivered by the intermediate code generation, that output is given sent to input to the code optimization process. So we'll accept, and what are the different techniques that are available in this phase optimization. So one of the main important basic blocks of optimization and peephole optimization techniques. It is, what are the different optimization techniques, peephole optimization, that we are going to brief overview of this subject. Now, here there are two types of basic block optimizations. Two types of basic. One is structure preserving transformations. Second one is algebraic transformations. Structure preserving transformations for the basic blocks, which holds, again, this contains different categories. The structure preserving transformations. One is common sub-expression elimination. Another one is dead code elimination. Common sub-expression elimination. Second one is dead code elimination. We have discussed several transformation techniques with this common sub-expression elimination also previous lecture. Now we are going to discuss some of the techniques which are related to this one. And many of the structure preserving transformations can be implemented by constructing a representation of basic block structure, that is DAG, direct acid graph structure. We are going to implement that. Algebraic transformations such as reduction in strength reduction. One of the algebraic transformation, the technique is strength reduction. And usage of different algebraic identities. We are going to use several algebraic identities. That means here this is an optimization technique where the involves the lot of process without holding this optimization process. We can achieve the concept of this optimization by applying these techniques very easily. For example, if you consider the arithmetic identity. So in case of algebraic identities, we are having the arithmetic identity. We know arithmetic identities such as plus, minus, star, slash. So these are the various arithmetic operations which we perform. See, for example, x plus 0 equal to 0 plus x, which is equal to x. So instead of performing this, we can apply this arithmetic identity. And this x minus 0 equal to x, and x star 0 equal to 0 star x, x star 1 star x, which is equal to x, and x divided by 1 equal to x. And these are all different class of arithmetic identities, and we are going to hold this type of identities and substitutable with the corresponding. Another class of algebraic optimization includes strength reduction. We are going to apply this strength reduction process by replacing a expensive operation with the smaller operation. Expensive operation involves lot of complex analysis compared to the lower ones. For example, if x star 2, which is equal to x star x, but here the expensive operation is x power 2. X power 2, the power is an expensive operation, but the cheaper operation compared to this one is star. This is a multiplication. So multiplication operation is very suggestible. Even by applying these replacement techniques, you have to verify whether this replacement operation leads to the same result or not. So before applying the expensive before and after applying. That is before applying x power 2, x power 2 result is same, which is same result as that of the applying the result of the x cheaper operation also. So x star x leads to the same result, but here operation is we have applied the operation power operation, and that is replaced with the multiplication operation. Replaced with the multiplication operation. So multiplication operation is able to perform easily computation compared to the power operation. So it is an expensive operation. It is a cheaper operation. Even though if you replace this one, the result may not affect. Result may not affect. And here the performance of the application, it doesn't degrade this one, and also the code, it is code optimization takes place in this one. So it is mainly the purpose of optimization code, which is called as strength reduction. This strength reduction, which comes under a technique of algebraic transformation. This is one class of algebraic transformation. And another one is we are going to apply, see here, 2.0 star x. 2.0 is a floating point number, and star is a multiplication and followed by x, which gives result x plus x, which is also same as. So here we are going to replace an operation, that is a multiplication, and this operation substitute with plus here 2x, which is giving here also x plus x 2x. The result, which is the same as that of the previous one. So here operation we are going to reduce. This is called as a strength reduction. Here one more example. Here if you see x divided by 2. X divided by 2. Here what is division? Division is an operation which is very difficulty compared to the multiplication. So x, which is equal to x star 0.5. That means x divided by 2, which is equal to x into 1 by 2. This x into multiplies by 1 by 2 means 1 by 2 means 0.5. So x means 0.5. So this x star 0.5, which is the same as x division by 2. So here the division operation is to be consumed start of time and takes a complex operation complex to compare to this multiplication operation, which is gives a same result, and then we are going to apply this strength reduction process very easily, replacing an expensive by a cheaper one. So that is comes under this strength reduction with the operation. Whereas we applied in arithmetic ideals also here x plus x star 1 star x. So instead of writing 1 star x star n, this is comes under as a multiplication. This is comes under as multiplication. But even if you apply or doesn't apply without x star 1, the result is x only. So the operation, the arithmetic identity, which is to be here we are going to see that the operation is involved multiplication not required compared to this result x. See here x divided by 1, which gives the same result as x, but we are going to use x without any operation. So expensive operations are to be avoided, so that the lot of difficulties, complexity, which are to be removed from this compilation point, which involves in the optimizations where lot of past is to be generated and the intermediate code is to be generated, and then this is to be strength reduction process are applied, and then it moves to the another phase of the cycle, compilation point, so that before producing the machine code we are going to strictly verify whether any possibility of effectively applying these principal sources of optimizations and observing transformations such as identities, arithmetic identities, and strength reduction process. So this is one class of this one, and another class of optimization is constant folding. This is also any one of the important strength reduction techniques, which is a principal source of optimization technique, where here we are going to evaluate an expression at compile time, and this constant expression replaced by another constant expression and by their values. So the constant expression which gives the same result. So for example, here the operation which you are performing 2 star 3.14. But here the what is the operation we are applying? Multiplication operation. So this constant expression evaluation can be done at the instruction level point of view, and this is replaced by the a constant once again, that is 6.25. So this is the expression is constant value 2 star 3.14, and in this there is a multiplication operation. We are going to eliminate and identified the and simplified by writing the another constant. So one constant expression. So evaluating the constant expression at compile time and replace this constant expression with another one, that is a suitable one, is called as constant folding. And also the relational operators such as less than, greater than or equal to, and these are all various operations which are going to generate unexpected common sub-expressions. Unexpectedly occurring some common sub-expression. Sometimes associative laws are also may be applied to common sub-expressions. How it can be applied to these associative laws as common sub-expression elimination means, see for example here A equal to B plus C one expression and E equal to C plus D plus B. Now the common sub-expression is to be eliminated. Here B plus C is common, A equal to B plus C and E equal to C plus D plus B. So here E equal to D plus B plus C. So here B plus C is the one of the expression, and once again we are going to, this is evaluated with the expression A equal to, once again for E equal to also another same B plus C expression is available. So we need to avoid that one at the time of intermediate code generation phase itself. We are going to avoid this elimination of the common sub-expression by implementing the procedure that is A equal to B plus C, which is written as the same string, but in the second string where is the commonality occurs D equal to C plus D. So here what is T? C plus D. Now we are going to put T plus B and write another expression E. So in that way we are going to eliminate this common sub-expression. Where the occurrence of this expression happens, find out and release this one with another intermediate. Say here a temp code T, temp variable T is allotted. A temp variable T is allotted, and this expression which is to be substituted at this where the point that is to be generated. So C plus D. This assignment can be representation with a temporary variable T, and this T plus the corresponding remaining sub-expression. So T plus B carried out another task, that is the final task, that is E. So intermediate expression which you have written is T equal to C plus T. So here suppose sometimes if the T is available, may not available, that is a requirement based on the application point of view. If it is not needed within this within the outside the block, then we can change this expression into a suitable expression, that is E equal to A plus D. So sometimes that is what is A equal to B plus C and E equal to D plus A, that is A plus D. So if the temporary is required or not required based on the usage of this particular block of statements, if that is not needed outside the block, then we can use these two statements. If it is needed outside the block, then we can make this as a temporary variable T, and then we can go ahead with the remaining parts of this program block of the statement. So this like this we can change the sequence of the statements by applying this associative laws, and this is laws to be applied with some common sub-expressions. Associative laws applied to some common sub-expressions. This also may leads to this several simpler solutions compared to these previous already allocated expressions. That is the common unexpected way of getting this sub-expressions that is to be commonly available in some of the expression, that is to be find out, and here that expression is B plus C. B plus C we are able to find out, then that is to be common for the two that B plus C equal to A, which is common to the first expression and also common to the second expression. So in the first expression we keep it as this, and the second expression where the commonality occurs B plus C, that is to be substituted with this one, and suppose if that is intermediately required outside the block, then you can use a temporary variable say t, and then you can make an use of assignment t equal to c plus d, and then you can proceed to the further execution of the task. And the compiler writer should examine the language specification carefully to determine what are the rearrangements of computations are to be permitted. Since computer arithmetics does not obey this identity of the mathematics, so we are going to evaluate sometimes the expressions such as the arithmetic operations involving star, plus, minus, like this. But instead of evaluating this expression such as x star y minus z, we can compute this one is x star y minus z. But sometimes if you evaluate a plus b minus c, but as a plus b minus c. So here computations are to be performed based on the evaluation of the parentheses, based on the hierarchy which is available. It is to be considered and then it evaluates. So b plus a plus and then b minus c as per the procedure requirement, it evaluates. Peephole optimization is a simpler technique, but it is a effective solution which is locally improving the target code. Is nothing but a peephole optimization. It is a method of trying to improve the performance of the target programming by examining the short sequences of the target instructions. So that's why it is called as peephole optimization. Here it is simply replace the instructions which are shorter or faster sequence wherever it is required. It simply replace the instructions, what type of instruction, and target instructions, whether it is performed or not. So they based on this main principle of the peephole optimization is that it improves the span of opportunities for the additional improvements. The performance of the target program can be improved by replacing this longer sequence with that of short sequence of the target instruction. So we will see what is that instruction point of view, which one is effective for this case of peephole optimization. There are several characteristics of the peephole optimizations. One is reduction, redundance, instruction elimination, flow of control optimization, algebraic simplification, use of machine idioms. These are the several characteristics of the peephole optimization. We are going to see each details one by one. So first one is redundant instruction elimination. So here the redundant instruction elimination, compiler is searches for the instruction redundant in nature. What is the instruction that is to be redundant? That is to be able to find out at compilation level. And sometimes multiple loading and sorting of the instruction, storing of the instructions also takes place. So that means here the multiple loadings are there, then that is to be removed. For example, here we are going to return the expression move x comma r naught. It is one instruction. Another instruction is written as move r naught comma r1. But we can delete this in the first instruction. What happens and rewrite the instruction. So here what is r naught? R naught means it is the storing the contents in x. So what x see here? That is move x comma r naught. That means what are the contents of register that is available in x. So here what is the r naught here? X only. So that's why r naught comma r1. So here the contents x and r naught. So these two which is available. But instead of taking a separate register and store the contents into that one, and instead of that we are not going to take this x. Simply we are writing the register r1, r0 and r1, so that the commonality, that is the loading of the things several times, that is to be avoided. Here r0 is to be loading once in the first, and then in the second 2 times it is loading. So here the multiple times of loading and storing the instance. So one time it is loading and storing, second time obtain the contents once again and perform the second instruction. That is to be removed in this case. And that's what here from these two instructions after deleting we will get the only one set, that is x comma r1. So here instead of r0 we are going to write x, and we are going to write the combination of two instead of two instructions we are writing only one instruction, that is x comma r1, so that we are going to avoid some loading and storing capacities, and then it can smoothly reduce the optimization process as per the requirement for this redundant instruction. So repeatedly executing the task. And another one is another important is unreachable code. So we have seen redundant instruction elimination, flow of control optimization, algebraic implementation, and use of machine code. So here, what is the unreachability of the code which arises? It is mainly unreachability code is a part of the program code, that is it never accessed. That means it is available inside the code, but it is not executed, or never accessibility is not available because of that written programming constraints, constructs which are available. And so here sometimes the programmer is to be accidentally written some piece of code, and this code is to be available and it does not execute to them. For example, here we have written a function add underscore 10. This is the function which we have written, but here in this function we have written x plus 10 and value of x. Here first initially we have written return statement. So what is the function? It is returning x plus 10. So what is the x we are supplied? With this return value it will supplying. So there is no chance of executing this printf statement. Printf never execute the printf statement, and as the program control returns back, here returns back to this control where, and printf can't be executed. So here we have to remove the statement, remove the printf statement. Why? Because even though if it is present, presence of the code even it doesn't execute. So that's why we are removing the code, this line of code, removing this printf statement. Even the removal of this printf statement, it doesn't affect the remaining lines of the code. But the presence of this code will unnecessarily increase the burden of the loadings and storage of the constructs, various other, and leads to the accessibility to other garbage collection systems, and various reference conflict arises with this one. So that's why this is an example of the source code where the lines of statements which are to be available, and this code is to be executed properly, and if that is required we can keep it this one. So here the printf statement which is available, if it executes the line of statements we can keep it. If the control doesn't goes, then it will not execute the statement. If the statement is not executed, so that lines of code is to be verified. Lines of code is to be verified. That is really executions for takes care of the executions for compilation point of view. And maybe sometimes we are going to write accidentally for other purpose. Then, but this is not reachable to the execution part, and the control accession is not available to this one. So here there is no accession points goes to this place. Like this of code to be verified each and every lines, and then we will come across this one and then verify the code. Thus, this code is called as unreachable code. Unreachable code. That means the statements are available, and certain points of the certain period of the time it exits, and while control comes to this control doesn't come to this place, and it never executes, and then simply stores, and this takes place lot of time. So that is the point to be verified. And another most one is flow of control optimization is one of the important. That is also a transformation that is optimization technique, where here there are several instances in a code, and the program control is jumps from one to another. But the performing the task is we are able to justify whether this performing or not without performing and jumping from there, and that's result is to be verified. So here the identify that jump, that type of jumps, and try to remove these jumps from that one. So the instances of code where the control is moving from back to next, and then this is fulfilling the requirement. Is it required? Verify. If not, then that is to be removed. For example, this line of code move or R1 comma R2. So here we want to understand, we are saying that go to L1. So here L1 means this line of code is to, and once again this piece of code here load L2, go to L2 and increment R1. So this is to be worked out. So here go to L2. So instead of going L1 and L2, we are going here jumping L1, jumping to L1. Here one jump is there with L1, and again jump to L2. So two jumps are there. So in order to, even if you jump to directly L2, this is doing the same task. So this piece of code is performing the same task as this one. So here two jumps are performed. Two jumps, here one jump. Here only one jump. So here this jump is required, but what is the result that is to be carried out with the two jumps, which is same as the result carried out with this instructions of the code also. But what happens here, the instances of the code where the program control jumps back to this one. So here go to L1 indicates that it jumps to section L1. Again go to L2, again it jumps to section L2. So instead of repeating several jumps, and that is to be in hectic task. So instead of doing that two times, we are going to write a direct jump from go to L2 and getting the result, same piece of result. So that is to be identified. Flow of control, where from which statement to another statement, where it is moving from, that is to be carried out. Is it really necessarily that is required? Then we can keep it. Suppose if that is not mandate, and trying to get some location storage instructions and memories, all this to be a lot of jumps, unnecessarily instance creations, all these are all very burden to this computing system point of view. So that is to be carefully observe, and then remove that jumps, remove that jump. So here go to L1, L1 go to L2. So we have removed this jump. Go to this, go to L2 jump, that is removed, and we keep it L2 as L2 directly, and then we have eliminated with the instead of two jumps, we have carried out the same task with one jump. So is it possible if the multiple number of jumps are required really or not? We have to find out that piece of code, and this flow of control is sustainable to carry out the result. Based on that, we can implement this process. That one of the main important technique that is called as algebraic simplifications. Here statements we have considered x equal to x plus 0, x equal to x star 1. These are all some of the identities which are formed, intermediate code generation algorithms which are to be used, and then that is to be easily eliminated with this by applying this Peephole optimization techniques. So previously I was in Peephole optimization techniques. So here it is an effective technique, and here the target code simply and effective technique for locally improving the target code. We are going to improve the target code. That is, what is the target code? That is machine code generated by the program instruction. So, and we are going to get the optimization performance, this target code, as we are going to examine several sequence of the target instructions. That is Peephole. We are examining the several target instructions, which is called as Peephole. Here, replacing the several instructions by a smaller set of instructions. So, long instructions are replaced with the smaller set of instructions. That means here two more instructions which are to be available, which does not carry out the task here. That is to be redundant instruction elimination. That is called as redundant instruction elimination. So, carry out the task with this type of instructions leads to the loading and storing of this space for the instruction point of view. So that's why we are going to remove. So this is the one of the important, that is peephole optimization. And here the code that is produced is an intermediate code which is coming from to the code optimization process, and these to be avoided, eliminated, and find out by applying this peephole optimization. Strength reduction also we have seen. The expensive replace the expensive operation by a cheaper operation. That means here the expensive operation is division x by 1, which is given to the x. So here we are going to apply cheaper, that means no operation here in this case. But here expensive operation is a division operation. So the replacement of multiplication with the addition. So x multiplication that is replaced with the addition operation. So x star x star 1 that is which is leads to the same result x star 1, which is equal to x, and x plus 0, which is giving the x. So here multiplication operation is there, which we have avoided, and we can perform addition operation, or addition operation also replaced with some other operations, like still some other level of the operation. We are going to try the availability of the possibility different things. So here, for example, x power 2 x square, and we have considered x star x. So here x square is to be considered and to be written. That is x power x 2 x square x power 2. So this computation requires an operation, that is power operation, power of operation, which is an expensive operation, that is to be the exponential case. This is an exponential operation to be removed with x star x. So that is to be considered as a replacement of super operation, that is multiplication. So compared to the multiplication, exponential is an expensive operation. So like that, sometimes a fixed point multiplication and divisions are also there. That is a power of 2, which is cheaper to implement than shift operations. And another example is floating point divisions by a constant can be implemented by a multiplication by a constant, which may be very cheaper. So like that, the floating point notations, multiplication, divisions compared with the shift operations and multiplication, we verify we are going to reduce as per the requirements, as per that, and reduce the and applying the technique. This is called as strength reduction. So minimize the strength, so that the evaluation of the expression going process very easily, and proceed to the next level of the instruction. So that's why here the level the result, so that the result doesn't affect even the replacement of that particular exponential with a multiplication operation. So a x power 2, which carries the same result with the x star x also, but here we are going to eliminate that strength of that the expression, that is power with the multiplication. So that is one of the example. Another one is fixed point multiplications. These are also takes very cheaper when you compare to the shift operation. So shift operations takes time, depends on that. We are going to replace that. And another one important one is machine idioms. Previously we have seen algebraic identities. Here machine identities depends on, we are going to launch or execute this compilation point. Several machines are to be run, or a machine can run with the help of the code that is to be available. But here, what is this target mission? So the mission maybe type maybe Windows or Linux or Sun Solaris or different type operating system may exist. So that machine carries with the hardware is set up with a different hardware setup. That means what is the features which are available in that Windows to Linux is somewhat different, and what are the operations which are performed that is effectively during the compile time. We are going to use this type of instructions, and we are trying to reduce the execution time. So as per that requirement as minimized by applying these techniques, this efficiently. So based on that, the optimization is to be very useful if you apply these type of techniques. And the operations such as auto increment, for example, auto increment, auto decrement, these operations are applied for the addressing modes, and some machines may have this auto increment and auto decrement modes, and these modes it improves the quality of the code. If you apply this code with the techniques latest, then automatically the performance usability increases, performance increases, and shorten execution program execution duration, that is reduces, and then efficiently getting the results. All these to be leads by applying this type of the procedures. So this is these are the um, different sources of optimization. That is principal sources of optimization. Redundant instruction eliminated, where the instruction is to be repeatedly available, that is to be flow of control. Optimization, different blocks which is just the same piece of code, whether you have to kept inside the block or if the temporary create the temporary and move outside the block. Algebraic simplifications, make use of some plus operations, x plus 0 and x star x, and replace use of mission items. So auto increment, auto decrement, there are different operations which are to be available, and you may depends on the requirement of the hardware specific instructions and operating system point of view are going to run with several instructions. So these are all the various optimization techniques which is used in the phase of compiler design of one of the phase, that is code optimization. In compilation point, the code optimization one of the phase where it requires this type of techniques, that is algebraic and this stand that is called as structure preserving transformations, and another one is algebraic transformation. So in structure preserving transformations itself, we are once again division, common sub-expression elimination, and dead code elimination. So common sub-expression elimination, which leads to the expression elimination, where the expression is to be getting executed repeatedly several times. The same expression executes repeatedly several times, repeatedly executing several times, repeatedly executing several times, and if that is not required, then we are going. So by this, in this example you have seen the this is, so here a plus b equal to b plus c. So here b plus c is executing once again in the second sequence of the instruction also, but that computation is not really required. Then that's why we are replaced with a two-step instruction, a equal to b plus c equal to a plus d. So this computation is removed, b plus c computation only one time, but here there are two times this computation. Here two times b plus c, one time is for first instruction, and second instruction here also b plus c. So two computations are there for b plus c. So here eliminated. So that expression is to be identified and evaluated and removed, so that the getting. Whereas in the second one, dead code elimination, the code that is which is available but not executed. See here in this one, the code is available but not executed in this type. So here printf statement, this dead code, unreachable code, where the printf statement is available, return statement. So here control goes back to the return statement only, but the printf statement is not executed. If that is not executed, not only this one statement, like that any other statements which are to be carried out which is unnecessarily increasing the length of the duration of the program and the variables and the storage, the conflicting references. All these to be leads to the different solutions. So that's why this type of unnecessarily unreachable code is there to be avoided. Unreachability. So this is code elimination. That code is to be available, find out, and then that is to be removed from the this instruction point of view, and then we are going to succeed with the results with the compilation or optimization point of view. So like this, there are um, different terminologies with the items are also there, machine items. So as per the hardware and software point of view, there is a mapping of the procedures which occurs along the different instrument point of view. For example, here the integer declaration with this Windows versus the Linux, the hardware setups which are different, and the storage space, we are going to resolve that type of the references. So where the flexibility and availability. So here, for example, auto increment addressing modes are available. That machines are to be easily suitable, and those type of the machines which easily carried out the task and then improve the performance of the applications. So these are the very important basic principles of this source of the optimization. These principles which are applied in the phase that is called as code optimization. Code optimization. This is one of the first phase, that is last but one phase of the compilation point of view, where we are going to put these procedures, that is common expressions elimination, algebraic simplification, strength reduction, constant folding. All these machine items, algebraic identities, constant folding to these sub expressions are to be eliminated, and takes lot of storage space. That's why after implementing we are going to get the code. So after implementing sources principle to sources of optimization, that is techniques, then the code that is delivered some code, that code is sent to code generation phase. So this phase, the whatever the code that is delivered, that is sent to code generation. So here the code generation, what is the code optimized phase, what is the code delivered, that is a improved code means that code is to be already processed with the implementation of this one, that is all the principal sources, algebraic forms, mission items, and constant folding, unreachable code, flow of control, structure preserving transformations. All the techniques are applied, and then the processed code that is to be available, and that code performance will be very improved and reduce the time. It reduce the compile time, execution time. What is the code that is to be executed? That time is reduced by implementing these principal sources of the optimization, and that code is to be sent to this code generation phase. Once again, in the code generation phase, there will be other techniques where it generates it leads to the machine code, that is called machine understandable code, which is easily getting the result, that is output of the program. So all the contents which are to be discussed, this available in the textbook, that is compilers principles, techniques, terms, that is Alfred City Ullman. And tomorrow will come next class will come up with one more new topic. Thank you once again. Thank you, all of you. We'll come up with one more new topic for the subject sensitive compiler design. Thank you once again. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.